We'll finish this chapter on linear systems by talking about applications of linear systems. I should mention there's tons of applications in physics and chemistry, and math and stats as well, obviously. You'll encounter these applications when you actually need them, and people will introduce the setup, the framework, and will help you translate them into linear systems. And they'll say, let's solve the linear system, and then blah, blah, blah. For instance, in physics, imagine you have a setup with ropes being tied together, and then you have these hanging weights sort of being balanced or in equilibrium, and your problem might be to find the tension in all of these ropes. Well, like you'll do that in physics, and you'll solve the linear system, and you'll get your vector of tensions in all of the ropes. And similarly, if we're trying to solve a bunch of other specific problems, because you'll encounter them whenever you need them in your specific fields, I'm going to leave them the care of introducing this in a way that would make sense in your fields. There's one instance that you're unlikely to encounter in your studies, but I think it's a nice application, or at least a nice illustration of how things work. So we will mention it here. And there's an application that's very mathematical, which is to say we try to find specific values of parameters that lead to certain things. One application that we will not talk about in this course, but that will prove to be very, very important, is to differential equations, in particular to systems of differential equations, linear systems of differential equations, or linear differential equations of high order, such as you might encounter in quantum mechanics and chemistry. Biology as well actually has a fair number of those. We'll leave that for the time being. Be aware, though, that if you encounter them, you need to have a smattering of an understanding of differential calculus. But you also need to be able to potentially solve things using numerical methods. Both of these are things we're not going to be touching on in this course. One extra thing you'll be needing, which we will talk about and touch on this course, is the idea of eigenvalues and eigenvectors. That's something we'll talk about in subsequent chapters. So these quantities, these objects, play very important roles outside of mathematics. Inside of mathematics, they do as well. So most of quantum mechanics, for instance, is basically closet linear algebra, with eigenvalues and eigenvectors having specific names or playing specific roles in the quantum mechanics, the allowed energies, for instance. Okay, but we'll pass over that because I suspect that some of you might not have studied differential calculus yet, and then differential equations a bit too complicated if you haven't done differential calculus at the very least. So we'll talk about network and traffic flows and testing scenarios. So the idea here is you can model the flow on a network by understanding its inputs and its outputs, and also by understanding how you restrict traffic between them. Now, traffic could represent a number of things. It could be something related to current through electrical system, circuit network. It could be cars through a road network, or planes through what do you call it, an airplane network. I'm not sure what you call that for real in English. But the idea is that if you know how many units enter the network and how many of them exit the network, then you might have some clue as to how the units propagate through the network, assuming you know something about the architecture of the network and its restrictions. So I'll give you an example which applies to cars in a downtown core somewhere. And because it's a downtown core, you often end up with one-way streets. Now, in practice, when a car enters an intersection, goes through the road associated with it, there's no real guarantee that it will leave at the next intersection, leave that road, right? It's conceivable that it was coming into park somewhere. Perhaps the person resides right here, so they enter and they don't actually leave the road network because they're not really going anywhere. They're not traveling through. You could argue then that, well, they might not be leaving the road network right now, but if they've entered here at some point, at some other point, perhaps a few days in the future, they'll leave again. So it's like, yeah, in practice, some of the constraints or the restrictions or the assumptions we're going to make aren't going to be satisfied. But we're making the assumption here that you have a network of one-way streets and that whenever a car enters the network, it has to leave the network at some point in the not too distant future. So any exception to that, we're just sweeping them under the rug right now. We're not really thinking about them. So you have 4 intersections, A, B, C, D, in this order here. And we have little arrows telling us the directions of the one-way streets. So let's say we know that 300 cars entered at A, 300 cars entered here at D from this location, and then we know that 100 cars left at B, and then 200 and 300 cars left at C. So what are the possibilities for the traffic X1, X2, X3, X4? How many cars per hour, say, would we expect to see taking these streets? So the arrows tell you the direction of the flow of traffic. The variables are the unknowns, the level of traffic on the streets in question. So how many cars per hour went on that street? So you can ask certain questions such as like, what's the maximum flow along the road AB? If it turned out that you blocked DA, if you blocked this road here for whatever reason, would there be a traffic jam? What if instead you were blocking BC for road work? What might happen? So we have a total flow in, which is 600. So it flows into the network. Like the network is this very simple square box here. 600 flows in. It just so happened to flow in. Just so happens to flow in 2 different locations. And then 600 flows out. It flows out on 3 different pathways. So everybody that's entered ends up leaving. Now, we assumed for all intersections what's called Kirchhoff's first law. The flow in is the flow out. Anything that comes in has to come out eventually. We solve this. Well, the 4 street segments that do not have known traffic flow, we call them X1, 2, X4. So at intersection A, the flow in would be, well, what's the flow in? There's 300 coming in from outside the network, and there's going to be X2 coming in from intersection D. Great. And what's leaving the network is X1. Or what's leaving the intersection A is X1. So we have 300 plus X2 is equal to X1. For B, you have X1 coming in, and then you have 100 leaving and X3 leaving. So X1 is going to be equal to 100 plus X3. At D, we have 300 going in, and then we have X2 plus X4 going out. And at C, we had X4 plus X3 going in, and 200 plus 300 going out. So you get this system here. Each intersection gives you an equation, and by the nature of the flow, these are all linear equations. And so if I rearrange the terms by putting the constant terms on the right and putting all the variables together, I get this linear system. This linear system dictates the flow, the number of cars that can go through the 4 intersections and the 4 segments of road that are open. Now we know a few other things, right? I mean, what are the possibilities? This is a linear system. It either has no solution, a unique solution, or infinitely many solutions. If it has a unique solution, then there's only one way for these vehicles to break down into each of these road segments. If you've ever done any driving, you know that that's probably not likely to be the case, right? But there could be no solution as well, right? It could be an ill-posed problem. Perhaps there's a typo in the traffic going in and traffic going out. Or there could be infinitely many solutions. There is one added complication that we don't typically have in linear systems. These x1s and x2s represent the number of cars per hour. And typically, you would expect that to be an integer. Now, there could be exceptions, right? What if you're measuring things over, say, 10 hours and you get, I don't know, 91 cars that went through a road in 10 hours? Then you might say, I'm going to divide 91 by 10 to get 9.1, and that's not an integer. That's acceptable. But in this specific context, we're assuming we're looking at what's happening inside of 1 hour. And so the number of cars per hour is really just the number of cars that go through the road. And you expect all of these things to be integers. It's not just that you expect them to be integers, they have to be integers. That's not a linear system. A linear system has no restriction on what values x1, x2, x3, and x4 can take. We're still going to treat it as a linear system for the time being, right? We have a system, we put it into its augmented matrix, and when we put it into its augmented matrix and we row reduce it, once again, I'm not actually doing the row reduction. You have to be able to get that yourself. You find that there are 3 leading ones, which means that there's one parameter. And this set here, this row here, is degenerate but consistent. So you end up with infinitely many solutions. There's a parameter S, let's call it. You can read the solution, but again, like I need to remind you, you need to be able to get this RREF. Nobody's going to be doing this for you on the final exam. If x4 is equal to S, this is what your x1, x2, x3, x4 solution vector will look like. 600 minus x, 300 minus s, 500 minus s, and then x4 itself is equal to s. So even if you don't think these things need to be integers, like let's say you end up with, oh, I'm just measuring a rate per hour, at the very least, all of these quantities have to be greater than 0. You cannot have anything here a negative number. There cannot be minus 7 cars going through a road per hour, right? So that does put restrictions. So the solutions here are not necessarily the solutions that you would expect to get from a full-on linear system. Because even though you've modeled a situation with a linear system, the restrictions don't allow for that to happen. That's often the case when you use mathematical models, right? Like first you model, then you get a solution, then you have to look at what the restrictions might impose because of the real world constraints. The streets are all one way, so we have to have xi is greater than or equal to 0. And when you implement these constraints, you find that 0 has to be smaller than s, has to be smaller than 300. It's impossible for s to be greater than 300. So it's impossible for the flow on X4 to be greater than 300. It's just not going to work. It's not going to work, right? Because you have 300 going in, then X4 of that 300 going from D to C. Well, if there's 300 going in, you could not have more than 300 going from D to C because there's no other way for cars to, enter that road here between D and C. So what's the maximum flow along AB? Maximum flow along AB would be this one here. What's the biggest value that X1 can take, given that X4 has to be between 0 and 300? This is what you end up with here, right? This has to be greater than 300 because 300 minus S has to be greater than or equal to 0. So 300, sorry, S has to be smaller than 300 because 300 minus S has to be greater than 0. If X4 then can be between 0 and 300, the smallest value that X4 can take is 0. The largest value that it can take is 300. But we're not interested in X4, we're interested in the flow for X1. So what's the largest value that X1 can take? X1 is equal to 600 minus S. And S is between 0 and 300. If S is equal to 0, then X1 had 600 cars going in. If S was equal to 300, then S is equal, X1 is equal to 300. So this thing here should actually be 600. If you block the road DA, so blocking the road DA right here is equivalent to imposing a restriction that X2 has to be equal to 0. If X2 is equal to 0, well, let's think about what it means here. If you block the road DA, there's no other path for the cars entering D to take in the network. They have to go through the road DC. So you have to have that X4 is 300. And then X2 was 0, which means that here the 300, X1 also has to be 300. And then 100 of those leave at B, so X3 has to be equal to 200. And then you have 300 going in and 200 going in, 200 going out, 300 going out. From a mathematical perspective, if you block X2, you're saying that 300 minus S is equal to 0, which means that S is 300, a given specific value, which means that all of the other flows, X1, X3, X4, have specific values. So there's no parameters. We get an exact solution. And it's 300, 0, 200, 300. So there's no parameters. Everything is fixed, but everybody who enters can exit. If you block BC for road work, you're saying here that this road is closed, then X3 becomes 0. If X3 is equal to 0, in the system, 500 minus S is equal to 0, which means that S is equal to 500. But that's a problem, because if you replace S by 500, your solution vector looks like 100 minus 200, 0, and 500. In order for this to happen, to be acceptable, you would have to allow two-way traffic on the street DA so that you can have some negative flow throughout that specific segment. It's a neat little way to to work things out here, right? Or the competing conclusion could be we can't change the one-way-ness of that road. So if you can't change the one-way-ness of the road, you cannot close BC for road work and hope for people to be able to leave the network. This is what this third conclusion is also saying.